Now we're going to be getting onto the next topic, which is piecewise functions. So piecewise functions are a combination of multiple subfunctions with restricted domains. So what we use piecewise functions for is if maybe we have a relationship that we want to describe, but it changes over time. We can't just use one function for it. An example of this might be if say your displacement with respect to time, say you are running at a constant speed for this period of time. You're doing a long distance race, you're running at a constant speed, and then suddenly you get to the end of the race, you're in the last 100 meters, and now you want to sprint. So now you speed up. You're no longer running at a constant speed, which means your displacement isn't increasing linearly. Now you're like accelerating, you're getting a lot faster, which means that now maybe your running looks like this. So in this scenario, we would need a piecewise function to model your displacement, because your displacement can't be modeled with just kind of one singular function. We need to model your displacement with multiple subfunctions. The other thing that you might notice is that I haven't then drawn the rest of this linear curve. And that's because, as it says up here, a piecewise function includes functions with restricted domains. So remember from the last section, the domain is the interval of x values for which a function exists. So I've only drawn those two functions for a limited interval. I haven't drawn the full things. Okay, now that was a very messy example. Now we're going to get onto actually how to draw piecewise functions. So, what we can see here is firstly the notation for piecewise functions. So for the notation for piecewise functions, we have this big curly bracket, and then we have each of the functions that we want to graph, and then next to them we have the domain. So this is going to be the x intervals for which the function exists. Now, it's really important that if you are expressing a piecewise function, that you do it using that notation. And then when you're actually graphing the function, what we need to do is we need to have a look at what the function is, and then what the interval is. So if x is less than 2, then we're going to have x squared. So it's even helpful sometimes to draw the function off to the side, just to kind of help visualize. So x squared is just a basic parabola that looks like that, right? So if x is less than 2, we're going to have kind of this interval in here. So this is going to be 2, and then our function is going to continue off in this direction, so we're going to draw an arrow. If x is equal to 2, then our function is going to be equal to 4. And if x is greater than 2 and less than or equal to 6, Then we are going to have 9 minus x. So drawing this off to the side, 9 minus x is going to be a function with a gradient of -1 and a y-intercept of 9. So, it is going to intercept maybe, let's say, here, and then come down at -1 like this. And its x-intercept is going to occur when y equals 0. When x equals 0. No, I was right, when y equals 0. I don't know what I'm thinking. When y equals 0, so we're going to have -x plus 9 x equals 9. So what that tells us is that our curve is never going to get to its x-intercept because we're only graphing it up until x is less than or equal to 6. So what it's going to look like is something like this. So we're going to have our intercept here at 9, and then the the value at x is equal to 6 is going to be -1 times 6 plus 9, which is going to be 3. And then of course the y value up here is going to be 4. And this is going to correspond to this section in here where we have the two functions meeting. Okay. And